I can say with confidence you've probably never seen a charger this powerful. A full 240 watts capable of adapting to devices from 5 volts to 48 volts. So how does it achieve such performance? Hello everyone, and welcome to the EEStar Reference Design Series. Today, we introduce a compact and highly efficient 240 watt GaN fast charging reference design from Leadtrend. It supports 5 to 48 volt output and fully complies with the USB PD 3.2 EPR standard. All key ICs, from the PFC stage to the AHB isolation converter to synchronous rectification and PD 3.2 protocol control, are provided by Leadtrend. This demonstrates their strong capability in delivering a fully integrated platform-based power solution. Leadtrend has open-sourced the entire demo package: PCB files, schematics, datasheets, BOM, transformer winding guide, and the full test report. Now let's take a closer look at its design highlights. PFC controller LD7593DA, paired with a Renesas 650V, 85 milliohm GaN switch, achieves up to 0.99 power factor, with excellent efficiency. The AHB stage uses the LD7710 controller, driving two Innoscience 700V, 140 milliohm GaN devices in an asymmetric half-bridge configuration for high power density and conversion efficiency. The synchronous rectifier LD7529U works with an Infineon low-gate charge MOSFET to minimize switching losses and maintain high efficiency across 5 to 48 volts. The protocol controller LD6618CQM, USB-IF certified for PD 3.2 EPR, supports AVS fine-step voltage adjustment and provides comprehensive protection. Next, we move on to live testing. We use two EEStar power collectors and one temperature collector, together with the Instra Helper software, to capture efficiency and thermal data. Efficiency is measured at 5 volt, 9 volt, 15 volt, 20 volt, 28 volt, 36 volt, and 48 volt, under both 120 volt and 230 volt AC input. For thermal testing, the device outputs 240 watts continuously for 30 minutes. Under both input conditions, we recorded the temperature curves of all key components. The data has now been fully collected. Let's first take a look at the conversion efficiency. Under 120 volt AC input, at 5 volts output, the efficiency is 87% at light load, 89% at half load, and 91% at full load. At 9 volts, the results are 91%, 90%, and 91%. 15 volts, 94%, 93%, 96%. 20 volts, 94%, 93%, 93%. 28 volts, 93%, 94%, 94%. 36 volts, 93%, 95%, 95%. 48 volts, the efficiency is 93%, 95%, and 95%. Under 230 volt AC input, at 5 volts output, the efficiency is 80%, 86%, and 89%. 9 volts, 83%, 89%, 90%. 15 volts, 88%, 93%, 93%. 20 volts, 89%, 93%, 94%. 28 volts, 93%, 94%, 95%. 36 volts, 94%, 95%, 95%. 48 volts, 95%, 95%, 95%. Next, we expose the demo board to open air at an ambient temperature of 25 degrees Celsius, under both 120 volts and 230 volts. We ran the unit at full power for 30 minutes and recorded the temperature of key components under 120 volt input at full load, with 48 volts and 5 amps output. The SR controller IC reached 69.8 degrees Celsius. PFC GaN MOS, 93.8 degrees. AHB GaN MOS, 107.2 degrees. Transformer, 79.5 degrees. PFC inductor, 62.2 degrees. Under 230 volt input, also at 48 volts and 5 amps. The SR controller IC measured 69.2 degrees. PFC GaN MOS, 72.2 degrees. AHB GaN MOS, 108.1 degrees. Transformer, 83.6 degrees. PFC inductor, 53.7 degrees. That concludes the test data for this episode. Thank you for watching, and we'll see you in the next one.